Thank you very much for having me. Today, what I want to discuss is a very fundamental question about effective field theory. And that's really just the question, which effective theories are good effective theories to use? So let me start by explaining what I mean by good and bad. So effective field theory is this framework that's very widely used in cosmology because it gives us a way to parameterize the small corrections that we would expect to see at low energies as a result of some unknown yet to be detected high energy physics. The idea is that you have all these different possible high energy models which have the same universal form at low energies. At low energies, they all just look like general relativity plus some small corrections. And the functional form of these corrections is fixed by the symmetry that's dictated for you, but they have an overall size, which is captured by these EFT coefficients, C1, C2, etc. So the idea is that all of this high energy information that we would like to learn about, it's kind of being packaged up for you very neatly in just a list of constant numbers. Okay, so those are the things that an observer, a low energy observer, would go and measure. And rather than commit to a particular high energy model, right, instead you can analyze your data using this very general and universal low energy description. Okay, so that's why it's so widely used, and I guess why it's so useful. Right? Because then as a theorist, right, as a model builder, you can come along and you can take your three favorite models and you can expand them at low energies, right? You can compute these numbers on the theory side and ask, where in this parameter space am I going to land? Right? So models that land near the data, those are favored. Models that land far away, those are effectively ruled out. Okay, so this is a very helpful framework which sort of bridges the gap between the low energy measurements you would make in cosmology and, you know, the kind of new fundamental high energy physics that we would like to probe at high energies. However, right, there's a catch, right? There's a problem. And the problem is that not all of these EFT parameters, not all values of C1 and C2 can actually be realized in consistent high energy models. Right? What that means is if you keep playing this game, if you keep starting from different high energy theories and look at where you land at low energies, there's some places you will just never land. Right? There's some regions in parameter space that are secretly unphysical. They might look like perfectly sensible low energy expansions, but when you actually try and go to high energies, you'll find that there's some obstruction or some obstacle that prevents you from doing that. So this effective field theory framework, okay, it's very general because it captures like all possible high energy models, but at some level it's too general because you've also introduced these large regions of parameter space that are secretly unphysical, that just don't make sense at high energies. So the goal of the talk today is really to explain how do we go about identifying and ideally removing these regions of parameter space that are secretly unphysical. Good. Now, this is not just an interesting academic question, right? This has a real impact on how we search for new physics in cosmology. So one example that I'm going to focus on later in the talk is a particular effective theory of dark energy, so some scalar field phi, coupled to the space-time metric g mu nu. Okay, the particular theory is a kind of quartic Horndeski theory. I'll write it down later. But the important thing is that in this theory, there are a couple of things you could measure. Okay, the fact that this dark energy field phi fills the universe and acquires some time-dependent background, it really acts like a medium for propagating gravitational waves. So the speed of very low energy gravitational waves in this effective theory can be different from one. Okay, so that's what's on the y-axis. On the x-axis is another observable in this theory. It's called alpha b, and it tells you how dark energy clusters on large scales. So if you have two fluctuations in the scalar field, how do they attract each other? And the contours here are the 1 and 2 sigma confidence intervals that we have coming from a variety of low energy cosmological measurements. So as promised in the title of the talk, right, the goal is to try and identify what regions of this parameter space are good, bad, and ugly. So the really important one, right, the focus of today's talk is identifying this ugly region, this gray region of parameter space, which is this region that corresponds to values of CT and alpha B, which might look fine at low energies, but actually could never be realized from any consistent, stable, high energy theory. And so I want to stress right at the beginning that that's subtly different to the usual kind of stability arguments that you might imagine making in the EFT. So for instance, the speed of gravitational waves, right, CT squared minus 1, it sort of seems reasonable that that difference shouldn't be less than -1, right? Because that would mean that you have some imaginary CT and that gravitational waves are horribly unstable at low energies. So clearly that region at the bottom is bad. But up here in this gray region, you know, for a low energy, if you just look at the low energy theory, you could have luminal gravitational waves and some small amount of dark energy clustering. There's no obvious contradiction, no obvious problem there. And so what I want to explain today is why there is secretly an obstruction at high energy, something that you don't see in the low energy theory, but which nonetheless we can show, we can prove is really going to be there the moment you try and embed this low energy Taylor series expansion into some complete high energy functional. All right, fantastic. So one reason that this is impacting our searches for new physics is that rather than fit your data using, you know, any old values of CT and alpha B, you could instead do this more refined fit where you say, oh, I'm going to use as a prior this theoretical information that Scott is giving me, right? The fact that there's no high energy model which could land in this ugly region, right? Maybe I shouldn't be fitting my data using that region, right? And if you instead fit using only the good values, then you get a much tighter constraint on these EFT parameters, right? You get a much better estimate of the sorts of deviations you might have from general relativity in our universe. Great, so the plan for the rest of today is to really explain how we draw that plot. Okay, so how do we decide what region of parameter space is ugly and couldn't make sense at high energies? And so I want to start with like everyone's favorite toy example, the simple harmonic oscillator, and show you how you could draw this plot already for a classical non-relativistic oscillator. And what that'll do is, I think, introduce all of the main concepts, because then when we go to talk about quantum field theories in cosmology, then the maths get harder, but the concepts don't change, right? It's the same underlying ideas. And then we'll apply those bounds, those constraints to the speed of gravitational waves and the rate at which dark energy clusters, and putting those together will make this nice plot that I showed you on the previous slide. Okay, and if there's time at the end, I'll say a little bit about some more recent work where we were exploring what happens if you look at different stable vacua for this dark energy scalar field. Okay, so let's start with the simplest thing you could imagine, a simple harmonic oscillator. So what you should have in mind is a mass on a spring, right? Now, one way to characterize this oscillator, right? You want to learn about this spring. You could characterize it by its response function or its Green's function, which tells you how it's going to move, how its position will change in response to some external force. So this is the thing that you would measure in an experiment, right? If I gave you a spring and I asked you, how does the spring behave? You would grab hold of one end and you would start, you know, yanking it up and down, and you would measure how its position changes, right? And so from that measurement, you can then reconstruct, right, from the ratio of the position to the force, you can work out this Green's function. All right. So theoretically, how would you calculate this response, this Green's function? Well, you would find it just by solving the classical equations of motion, right? You know how the spring is going to respond in response to a force. You have Newton's second law, right? You know that the acceleration is going to be equal to all of the forces acting on this mass. There's the external driving force F. There's the Hooke's law that tells you how the spring is resisting the motion. And then you could also have some kind of frictional forces, this gamma V term here in the middle. So in frequency space, this is then a very easy calculation to do, right? If you Fourier transform this equation, all of the time derivatives just become I omegas, right? And then the Green's function, the thing which we would need to put into this definition at the top, would just be the inverse of this classical equation of motion. Okay, so this would be the full story if you had an ideal simple harmonic oscillator that really behaved exactly like Hooke's law tells you it should. But of course, real springs don't just obey Hooke's law, right? They actually have all kinds of more complicated interactions. Right? They have higher order terms. They have terms that have more derivatives acting on X. And in general, trying to then invert this equation of motion and find G becomes an incredibly difficult problem very fast. So the effective field theory logic, right, applied to the simple harmonic oscillator is to say that if these interactions have some characteristic frequency lambda, then I can Taylor expand their effects in the response function. Rather than solve the full complicated problem, what I can imagine doing is just Taylor expand G, or rather Taylor expand 1 over G, in powers of omega divided by this scale lambda. And so as long as I look at very low energies, much smaller than whatever characteristic frequencies determine these interactions, then this is going to be the answer. It doesn't matter how complicated the spring actually is, my low energy response is always going to look like this. So that's great because now, right, if you're doing slow forces, low energy forcing, you have this universal functional form that you can fit to data. So you do some experiments with your spring and you find, say, the 1 and 2 sigma contours lie somewhere in this parameter space. So the question that we've really set out to answer is, are all of these values equally good? Right? For a real spring, can you have arbitrary values of omega naught, gamma, C3, C4, or are they secretly connected in some way? So the answer is going to be that they are secretly connected in some way, and let me tell you why. So suppose we take the spring, right, and we perturb it with a force at a particular frequency, okay, some monochromatic forcing, right? And the reason that we're going to do that is that by definition of this Green's function G, the frequency space Green's function is precisely the thing that tells you how the position responds. But with these two simple expressions, right, you can use more Newtonian mechanics to work out things like how the energy of this mass is changing in time. Okay, so you know that the work done is the force times dx, the force times the change in the distance. So the rate at which the energy changes is F times x dot, right? The dot brings down a factor of omega. There's two factors of F naught, one from the F and one from the x. And then this real part becomes an imaginary part. Okay, so it's a very simple calculation that you can almost just do in your head in real time. The rate at which the energy changes in the spring is proportional to the imaginary part of G. Good. So that's the really first kind of important thing to know about response functions in general, right? This is going to turn out to be a very general feature of any response function. If you want this oscillating system to be stable, right, then this imaginary part has to be positive. Now let me explain why these two things are connected. If the imaginary part were negative, what that's telling you is, as a result of this forcing, you're decreasing the energy, right? That means that something about the system was unstable to start with. If you were in some stable minimum energy configuration, then any kick that I give the system ought to increase the energy, right? But if the imaginary part of G is negative, it's saying that by doing this harmonic forcing, I'm able to decrease the energy and make the system more stable. So it was clearly unstable to start with, right? That's the idea. Okay. Good. So we have this constraint, right? For the system to be stable, this imaginary part has to be positive. And so the simplest thing you can do with this constraint is you can use this Taylor series expansion that I wrote down on the previous slide. Okay, at low frequencies, this G has to just be some Taylor series expansion in powers of omega, and the imaginary part of that Taylor series has to be positive. Okay, so at low frequencies, all the interactions you can ignore, and that's basically telling you that the friction, right, the coefficient of friction in the spring has to be positive. Right, so that this is the sense in which some region of your parameter space you can immediately label as bad. This is a region that would be unstable already at very low frequencies, right? Already just in this effective description, expanding G at small omega, you can see that there would be a problem if the coefficient of friction were negative. It would be telling you that you can, destabilize the system with some small harmonic forcing. Good. But we can do better, right? Because this is a condition that really should apply at any frequency, right? We don't want it to be the case that at some high omega, the system suddenly goes unstable if you give it a bit of a kick. So there's a lot more constraining power in this condition. The issue, right, is that at very high frequencies, we actually don't know what this G of omega is. Okay, the whole reason we had to do this effective expansion at low omega is because we don't know how to compute this thing at high frequencies. It depends on the complicated details of the interactions. But, okay, however, we can use the following trick. Okay, and the trick that I'm about to describe, it really is the trick that underpins the whole modern positivity program, right? The whole of the rest of this talk and numerous recent papers deriving positivity bounds on effective field theories. Okay. The trick is the following. You might not know what this function G is at very high frequencies, but there is something that you do know, and that's that the position of this oscillator, the way it's moving, should only depend on things that have happened in the past, right? What that means is this integral that you do over t prime shouldn't know about the force in the future. It should only know about the force in the past. And so that's telling you that this response function has to vanish, right, whenever this argument is negative, whenever t prime is bigger than t. So this condition is now not really a stability condition. This is now coming from causality, the idea that only the past affects now, right, and the future doesn't affect now. So this is a really powerful condition, right? This is telling you that this function g of t, right, has to vanish for all negative arguments. It's telling you quite a lot about this function now. It can't be some random function. It has to have this special property. So if you Fourier transform this equation, right, and go from the time domain to the frequency domain, what will you get? Well, you'll get the following equation in a box. It's called the Cramer's Kronig relation. And really what it's telling you is that there is some integral that you can do over the imaginary part. And the effect of this integral is to remove the imaginary part. Okay, it's for the oscillator quite an easy thing to prove because this particular blue integral that we're doing, right? You can ask Mathematica, what is this blue integral of a sine of omega t, a sine function, and this blue integral turns a sine into an e to the I omega t times the sine of t with a g, right? Whether t is positive or negative, you will get plus e to the I omega t or minus e to the I omega t, right? But now, because g is a causal function that vanishes for any negative argument, it doesn't matter. This plus or minus sign is always plus. So it's easy to show right? That this special integral that we're doing really just removes the imaginary part. It turns the sine of omega t into an e to the I omega t. All right, good. But for us, what does that mean? Well, here on the right-hand side, now we can do our low frequency Taylor series expansion, right? We can expand this G on the right-hand side in terms of these C3, C4 parameters. And causality says that those numbers, they have to be equal to this integral up to arbitrarily high frequencies, right, of the imaginary part of G. So if you want this oscillator to be stable at any frequency, then this integral is the integral over a positive thing. It's the integral over the imaginary part of G, which we argued had to be positive. And that's telling you that all of the coefficients in the Taylor series expansion of G, those are all positive numbers. So if you take the expansion that I wrote down before, right, and you just look at the fourth coefficient in this Taylor series expansion at low omega, you'll find some bound, you'll find some constraint as a result of causality and stability, which relates C4, which controlled the interactions, to parameters like gamma that controlled like the damping in the spring. Okay. So now this gives you some function, right? Some line that you can draw in parameter space. And the idea is that when you satisfy this bound, then everything's hunky-dory. You can be stable at arbitrarily high frequencies, no problem. But if you violate this bound, if C4 gets too small, then you would be in this ugly region where the low energy expansion looks okay, but causality guarantees that when you go to high energies, at some point, things are going to become unstable. At some point, this imaginary part of G is going to flip sign, right? So here I've drawn kind of what it would look like in practice, right? If you were to plot the way the energy changes in response to a forcing, at low frequencies, it's just determined by gamma and the other EFT parameters. But as you go to higher and higher frequencies, you'll see this divergent. Different models will have very different behavior. And in this ugly region, the idea is that all high energy models that are causal, they will all at some point go negative. Right? So that's the sense in which this is like an unphysical region of parameter space. There is no causal model in which you would have a stability to arbitrarily high frequencies. Good. So before we do positivity in quantum field theory, right? Let me just make one thing very clear. And I think this point is not often stressed either in papers or in talks. Here, this is a positivity bound. This is a bound coming from causality and stability, which constrains the EFT coefficients of a non-relativistic classical oscillator. Okay. I'm about to show you the analogous bounds on a Lorentz invariant scattering amplitude. But the fact that it's a quantum mechanical amplitude and the fact that it happens to be Lorentz invariant, those are sort of minor details, right? The kind of constraining power, the whole theoretical construct is really causality, so that there's some relation between the low and the high energy regimes, and then some notion of stability, some constraint on the imaginary part of your response function. Those are really the only two things that you need in order to run this argument and carve up your parameter space into regions that could make sense at high energies and regions that could not. All right, good. So now let's ask what would happen in a quantum field theory, okay? And this will give us bounds that we can then directly apply to theories of dark energy in cosmology. So now, rather than the position x of t of the spring, you have the scalar field operator phi of x. It's now not just a function of time, it's also a function of space. So it just lives in all of space-time. But you could imagine doing the same sort of experiment, right? You could imagine that, you know, in some region of space-time, you turn on some sources, right? Some driving force of the system. And then you ask, if I then measure the field at some later time, what is the expected value of that measurement, given that I've turned on a particular source J? And again, you can define a response function, and it tells you how these two things are connected. So diagrammatically, we sort of draw it like this. You imagine that there's some sources in the past which could produce these scalar field fluctuations that you would then measure at some position x. Okay. Good. So same story applies, right? It's exactly analogous to what I just told you. Finding this Green's function is a very difficult problem in general. Okay, the equations of motion for this scalar field that you're trying to quantize, they're some complicated nonlinear thing that have arbitrarily high time and space derivatives. Okay, solving this problem exactly is a nightmare. However, when you're at very low momenta, right, if you go to momentum space, then you can do the same effective field theory expansion, right? You imagine that the interactions have some characteristic energy lambda, and as long as I'm at momenta much below that scale, then this Green's function has to just look like a Taylor series expansion. It can't look like anything else. Okay. So you can repeat exactly the same steps, right? You can appeal to causality, which says that this thing has to vanish when the measurement and the source are not causally connected. And stability, again, tells you that the imaginary part of this G has to be positive. And so, again, you get this constraint that this coefficient C4 is bounded by some of the parameters that appear at lower order. Okay, in this case, it would be minus lambda squared over m squared. So this is arguably the simplest positivity bound that you could get in a quantum field theory. But it's not the one that I used to make the plot at the beginning. And the reason is that, unfortunately, this constraint is often quite a weak constraint, right? Especially in cosmology, if this was supposed to describe dark energy, the mass of the scalar shouldn't be more than the Hubble rate today, roughly. But the characteristic energy associated with the interactions, that'll know about the Planck mass. That will be something gravitational in nature. So this ratio will inevitably depend on something like m Planck divided by h. So this bound is just telling you that C4 is greater than minus some huge number. And so it's actually not going to be so useful for dark energy. But what we can do instead is just go to the next order. Okay, rather than ask how does a single measurement of my scalar field depend on the source J, I can ask, what if I do two measurements, right? If I measure the field at some place x1 and some later place x2, how are those two measurements correlated with each other, right? And there's three contributions to this correlation function. You can draw them in diagrams. It's maybe simpler to look at the diagrams than the equation. The first diagram tells you that these two measurements can affect each other, right? In quantum mechanics, if you do a measurement, it disturbs the state. So my first measurement can affect my second measurement. And that doesn't care about the source J at all. That's just a result of doing two consecutive measurements in quantum mechanics. There's then a term that looks like this source J producing two separate unrelated fluctuations that I then measure at some later time, right? And then this correlator just factorizes into the product of the two one-point correlation functions that I described before. But now the really interesting term, the term which is going to be useful for us, is this final term, which depends on two J's, and then it has a nonlinear Green's function, which I've called f. And the idea behind f depends on four arguments. It depends on the two places that you make the measurement now, and the two places where the source produced fluctuations in the past. And the idea is that this piece captures all of the interactions, all of the ways in which these two fluctuations could have been produced and then interact with each other, collide with each other, exchange other particles in the theory. Ultimately, they become correlated, mixed together, they know about each other. Good. So again, in momentum space, right, if we were to Fourier transform in these four arguments, we would find that this response function, this nonlinear Green's function, has a very particular form. If this theory is invariant under translations, then there's always going to be some delta function which enforces the conservation of momentum. That's just a result of the symmetry. Also, looking at this diagram, right, these interactions have two fluctuations coming in from the past and two fluctuations going out to the future. And so each of those legs of this diagram are going to look like one of these linear Green's functions that we wrote down before. So you can strip all that stuff out, and what you're left with is some residual part, which we call I times A. A is the scattering amplitude, and in terms of these diagrams, it looks like just the interactions that you have in your space-time with all of the external legs kind of chopped off. All right, very good. So this thing is, again, a very difficult thing to compute in the full interacting theory, right? Computing this even in perturbation theory is quite challenging. But if these interactions have some characteristic energy scale lambda, then you can, expand this amplitude in powers of the energy divided by lambda. Okay. Now, because this is a relativistic theory we're talking about now, what energy should we use? Well, the energies that we often use are these Mandelstam variables S and T, right, which are some Lorentz invariant products of P1, P2, and P3. And there's a simple counting that you can do to convince yourself that you only need 2 of these energies, right? It might look as if this function depends on 16 things, right? Each of the 4 components of 4 momenta. But in practice, this delta function kills 4. These 4 external legs, okay, these G's are very sharply peaked when P squared is close to M squared. Particle physics, we say when the particles are on shell. So that kind of removes another 4. And then you have 6 symmetries, right? If you're invariant under boosts and rotations, right, the 6 Lorentz generators, that would remove another 6 variables. So that's why you only need S and T. Okay, good. But the thing to take away from this slide, I guess, is firstly, what is the scattering amplitude? This scattering amplitude is telling you how, if you measure the field in 2 places at late times, how is that connected to sourcing that you did in the past? And its EFT expansion has these undetermined coefficients, which again, you can go away and measure as a low energy observer, do some low energy scattering, measure these numbers. Okay, and that's capturing all possible interactions that this theory could have. But before we actually, go ahead and try and fit these things to data, right? I think the question we should always be asking ourselves is, can these coefficients, can they really take any values? Should we have some uniform prior on this parameter space, or are they somehow constrained? Okay. And they are constrained, and they're constrained for exactly the same reason that the oscillator was constrained. It turns out that if you want this system to be stable, then the imaginary part of this amplitude has to be positive. And the reason is now it's no longer an energy argument. It's not that the source changes the energy of the oscillator. Rather, now it's quantum mechanics. What happens is the source changes the probabilities in the system. And what you want to make sure is that the probabilities in the system are all positive. If the probabilities became negative, that would be signaling some weirdo instability, right, in this quantum mechanical system. So there's a particular probability that you could look at, right? You could ask, what is the probability that we would measure changed momenta? If the source produces 2 particles with momenta P1 and P2 in the past, what is the probability we measure some different momenta at late times? And that is equal to 1 minus the probability that the momenta stays the same. And what is that probability? It's the mod square of an amplitude, right? The amplitude is 1 for the particles not doing anything, and IA in this limit t equals 0, which is the probability that the particles interact, but those interactions just so happen to preserve the momenta. And if you expand out this mod square, you'll find that it's the imaginary part of A and its mod square, which determines this probability. So if this probability has to be a positive number, it's telling you that this imaginary part has to be bigger than the mod square, which is a positive thing. Okay, good. So this is the first kind of key ingredient that we needed, right? We needed that this response function, this amplitude A, has a positive imaginary part. And indeed we do. It just follows from positivity of probabilities. The second ingredient that we need is causality, is some way to connect the low energy expansion to the high energy imaginary part. And again, it's exactly the same story, right? This response function vanishes when these points are space-like separated, right? Because they're not in causal contact. And you get something which is exactly the same as the Cramer's Kronig relation conceptually. It's just mathematically this blue integral that you have to do is now a bit more complicated. But what it's doing is giving you a way to connect, right, the amplitude, say at very low s and t on the right-hand side to an integral on the left-hand side up to very high s. Good. So this gives you a way to diagnose, just by measuring low energy scattering, whether there is some funny instability, negative probabilities at high energies. Okay. In particular, this coefficient of s squared in the expansion of the amplitude has to be a positive number. All right, good. There's a technical note written here in gray, which is that you might ask whether these integrals always converge, because I'm integrating this amplitude up to infinity. And actually, you can see if the amplitude was just a constant, this integral wouldn't converge. It would look like ds prime divided by s prime, and that diverges logarithmically. So what we actually need is a third ingredient, which is locality. And that tells us that this amplitude is really bounded at high s, like s squared. And so we're guaranteed that this integral will converge whenever we take two or more s derivatives. Okay, good. So that's a somewhat technical comment, which is designed to explain why these bounds really start at the SS coefficient and don't apply to the lower order like C0 coefficient. Okay, good. Great. So this idea that you can use causality to connect high energy conditions with EFT coefficients, this has led to a number of new constraints on EFT parameters, on scattering amplitudes. So this is not a comprehensive review of these positivity bounds. This is just to explain how we made that plot at the beginning. So how did we make the plot at the beginning? Well, we needed to use two bounds. There was a bound that this s squared coefficient is positive, and the other bound comes from relating the coefficient of s squared t to the coefficient of s squared. Okay. But it follows from exactly the same logic. You take this relation between the low and the high energy amplitude, and now you take 2s and 1t derivative, and you massage it a bit until you can write it as a bound between these EFT parameters. Good. The other thing which is worth commenting is you might say, okay, these bounds are lovely, but at the moment it seems like they only apply when you have Lorentz invariants, because that assumption kind of crept in when we use these variables s and t. And so I wanted to comment that recently there's also been a lot of progress in understanding how you might generalize these arguments to cases where you give up some of your Lorentz invariants. When you break some of your boost invariants, you can actually write down very analogous bounds. Okay, good. So finally, right, in the final five minutes or so that I have, I want to bring it all together, right? This is now hopefully given a very clear picture of where these bounds come from, what were the inputs, and how would you compute them. So let's do it in this particular example. So we're going to describe a dark energy, and that's of course a very difficult problem. But at low energies, we can use this EFT logic. We can expand the action in powers of the fields and their derivatives. And in particular, if we assume certain symmetries, in this case, diffeomorphism invariants, and the following two symmetries for the scalar. The scalar should be invariant under a Galilean symmetry. So you shift phi by a constant and then a constant times x. And also a Z2 symmetry, which means you can only have even powers of phi in the action. It turns out that this set of three symmetries are incredibly constraining. It basically pins the leading interactions that you can have between the metric and the scalar phi to be something like this, right? To be of this functional form. This would be called the quartic shift symmetric Horndeski theory. Okay, so it's a particular theory that tells you how phi and its derivatives couple to the metric g mu nu, which lives inside R and also inside an overall metric determinant that sits outside the Lagrangian. So the phenomenology of this theory is well understood. So roughly speaking, the way to think about it is that this P of X This is the thing that determines how the background evolves. And by choosing a P of X appropriately, you can arrange for something that looks a lot like lambda CDM. And this function G4 and its derivatives, they control how perturbations, how small perturbations on top of this background evolve. So the two observables that I plotted at the beginning, right, the frequency of gravitational waves, sorry, the speed of gravitational waves at low frequencies, this is really determined by the first derivative of G4. And the rate at which dark energy clusters on large scales, this alpha B, okay, it's some function, but the important thing I think to take away is that it's really the second derivative of G4. Okay, so when we talk about measuring CT and alpha B, really what we're measuring from this EFT point of view is the first and second derivatives of G4. Okay, good. So what are we going to do, right? The idea is to take this particular EFT of dark energy, right? That's our starting point. And we're going to focus on theories in which this P of X has a nice stable lambda CDM background, right? Some cosmologically relevant background, but it also has a stable flat background. So it also has a background in which phi equals 0, about which we can expand. And the idea now is to say, well, let me do this calculation in two steps. First, I can expand around the flat background where things are Lorentz invariant. I can compute these amplitudes. And I can run these positivity arguments, right? If I compute these amplitudes, I'll find that in order to be stable at very high energies in any causal theory, I need the first derivative to be positive. And I also need the second derivative to be bounded in terms of the first derivative. Good. So now we have constraints on this function G4. So we can go back up to our effective field theory, and we can now instead expand around the cosmological solution. Right? And when we expand around the cosmological solution, we'll find this phenomenology, right? That the gravitational waves now have a non-trivial speed and the dark energy clusters in some non-trivial way. But these bounds that we derived, right, now translate into conditions on CT and on alpha B, right? Because the first derivative of G4 is just controlling CT, and the second derivative controls alpha B. Okay, so this is where these bounds come from, and this is how we go about carving the parameter space up into regions that are good and ugly. Fantastic. So that I don't overrun too much in time, let me bring up the plot that we had at the beginning, and say a few words about what these bounds mean. So the first bound on the speed of gravitational waves, right, comes from scattering, this kind of scattering process where you scatter phi against the matter field. And because phi and the matter both couple to the metric, right, this scattering process knows about how G and phi interact. And that's why it's telling you something about how the gravitational wave speed would be affected by a time-dependent background for phi. And now it's pretty interesting that these conditions, right, causality and stability at high energies, they're really translating into this condition that these gravitational waves should travel superluminally, should travel faster than any matter fields. So what that means in this plot is that when CT squared minus 1 is positive, that would be, you know, the good region that satisfies this positivity constraint, that this coefficient CSS is positive. And there's an ugly region where you violate these bounds. So these like slightly subluminal values of CT, they look fine at low energies, but they're secretly sick at very high energies. And then finally, if CT becomes complex, that you don't need any fancy positivity arguments. You can already say that that theory is bad just by looking at the EFT. Good. But then we can do a bit better because we can also scatter phi with phi. And again, we'll get some amplitude that now depends on s squared t. And so we can use that second positivity bound that relates this coefficient. Good. And so now the second derivative of G4 is bounded in terms of the first derivative. And so plotting this function, right, in this parameter space carves up the remaining superluminal parameter space up into regions where alpha b is small enough to satisfy this bound, and alpha b is too large to satisfy this bound. And so, so this hopefully kind of closes the loop now. So now we've started from this figure, and in particular, the points that I want to close on today are that now that you've identified, right, the regions of parameter space that are good, bad, and ugly, then there's lots of interesting things that you can now do with this map of your parameter space. The first kind of very important thing that you can do is impose, right, stability and causality as a prior, right? From a Bayesian point of view, you could say, well, I have a pretty high degree of belief that the universe should be causal, and that at high energies I want probabilities to be positive. Those seem like quite reasonable assumptions to make. But if you are committed to those principles, right, then a Bayesian would tell you that there should be some prior on your parameter space that says you can only take values in this green good region, right? So if you redo the fit, okay, the two colors here to pay attention to are yellow is without any priors, and black is with both of the priors. Red is with only one of them. What happens is you really shrink the size of this region, right? So if you look at the 1D posterior, right, let's average over the gravitational wave speed, then this is what you find, right? You started with some kind of Gaussian that was fairly broad, and as you impose these positivity bounds, as you introduce this new theoretical information, you're making this width much narrower. You're getting a much better estimate of the size of alpha b. Good. And so the final thing that I want to say before we move on to any questions is that you could also run this story in reverse. Okay, so here point number one is saying, let's start in the UV, let's start at very high energies and assume that we have causality. What does that mean at low energies? And running this in reverse, right, you could say, well, if next generation surveys really shrink these contours, okay, give us a much better estimate of CT and alpha B, this tension could develop, could get a lot worse. If these contours shrink and land you somewhere, in this lower right quadrant, which is very far from the good region, what would that mean? That would be telling you something mega profound. That would be telling you that whatever high energy theory completes dark energy, it isn't causal, right, in the way that we usually expect in a local quantum field theory. Or that quantum field theory is somehow not the right framework and probabilities are allowed to be negative for some as yet unknown reason. Okay, good. So I'll stop there. So thank you very much for your time and for your patience with me running a little bit over. So I'll hand it back over to the organizers for any questions.